So now we have seen the application for the uniformly distributed load and the uniformly varying load. So now we will see how to convert this UDL or UVL into a point load. Okay. So without converting UDL and UVL into point load, you cannot do the uh, calculation to find out the support reactions. So first we will see how to convert UDL into point load. So suppose one beam AB, it carries the UDL, that is a uniformly distributed load, like this. And its intensity for this UDL. So UDL is always represented as an intensity. So this is W Newton per meter. Okay. Or sometimes UDL can be shown like this. Okay. So this is also UDL. So this is W Newton per meter. So whenever you find out the support reactions, okay, we have to convert this into a point load. So the conversion is, this is the span of the UDL. Let us take this total distance as a L. Okay. So UDL always act exactly at the center of the span. Okay, that is a point load due to UDL will act exactly at the center. So this is the point load because of UDL. So it will act at distance L by 2 and L by 2. Okay. Now this magnitude of the point load due to UDL, this is equal to the intensity into this span. Okay. So whenever we convert intensity into point load, finally we should get the unit as a Newton, because point load has a unit Newton. Okay. So here you can observe W into L. Okay. So W has a unit Newton per meter and L has a unit meter. Okay. So finally you will get the unit as a Newton. Okay. And this Newton means this is the point load. So always remember, for the UDL, just multiply the intensity by its span. Okay. So this is nothing but the point load because of UD. And this point load act exactly at the center of the total span. Now second is conversion of UVL. So UVL into point load. So we have the UVL like this. So this is the maximum intensity. So this is equal to W Newton per meter. Okay. So here W I have taken as general value. So it can be 10 Newton per meter, 20 Newton per meter. Okay. Or sometimes this value can be given as a Newton per millimeter. At this point, we have the minimum intensity. So that intensity is 0. Okay. And this is the span of the UVL, which is the L. Okay. Now, while analyzing the beam, that is to calculate the support reaction. Okay. You will convert that UVL into a point load like this. So point load, because of the uniformly varying load, it will act at this point, not exactly at the center. Okay. So actually this point load, it acts. So if you observe this, this is a triangle. Okay. So it acts through the center of gravity of that triangle. Okay. So this is the center of gravity. So this point load, it will act at the center of gravity, and this distance with respect to this 90 degree. Okay. So this is equal to L upon 3. So always remember, distance of point load in the UVL with respect to the 90-degree angle, it is L by 3. And from other angle, so this is the acute angle. Okay. So this will be 2L by 3. So finally, this addition, it will be L. Okay. So suppose the beam is AB. And this value, that is the magnitude of the point load, this is given by this equation. You have to just use the area of triangle. 1 by 2. This is the height. Okay. So height is given as a maximum intensity, which is the W, into the base, that is nothing but the span. So W into span. Okay. So for this is the 1 by 2 W into L. Okay. So if you observe here, finally you will get the unit as a Newton only, because W is Newton per meter and L is meter. Okay. So unit will be Newton. So this is the conversion of a uniformly varying load into the point load. Okay. So once you convert the UVL into point load, then you can do the remaining calculation to find out the support reaction. Okay. And sometimes the load, it can be the combination of a UDL and the UVL. So if we have the loading, which is combination of uniformly varying load and uniformly distributed load, then how to convert that into a point load? So suppose we have one beam, which is a AB. Okay. So it is supported with the help of UDL. And this UDL, it has an intensity, which is a W1. Okay. Newton per meter. And just above this UDL, we have UVL like this. So here two types of loads, they are simultaneously acting on the beam AB. And this is having the intensity. So this total intensity from this point up to this point, it is given as a W2 Newton per meter. Okay. So for this conversion, first find out this side. Okay. because this initial side, that is the intensity for UDL, it is given as a W1. Okay, so this will be W2 minus W1 Newton per meter. Now this will be the height or the maximum intensity for the UVL. Okay, and this is the intensity for UDL. So you can convert. So you can write here F1. This is the point load due to UDL. Okay, so this will be W1 into this total span. So let us take this L. Okay, so W1 into L. This is the point load due to UDL. Then F2, this is point load due to UVL. So this will be 1 by 2. Now height of the uniformly varying load is W2 minus W1 into total span of the uniformly varying load is L. Okay, so this is Newton and this is also Newton. Okay, so we have converted varying load and the distributed load into corresponding point load. Okay, now next is we have to show that point load on the beam AB when we draw the free body diagram. So we will convert this actual loading into free body diagram. So this is the beam AB. First, show the point load due to UDL. Okay, so it will act exactly at the center of total span. So this is at distance L by 2, and this intensity will be W1 into L. That is the magnitude. Second is F2. So this is equal to 1 by 2 W2 minus W1 into L. So it will act somewhere here. So this is W2, sorry, 1 by 2 W2 minus W1 into L. Okay, and this position is at distance L by 3 with respect to this 90-degree angle. Okay, so this is the free body diagram for the given combination loading UVL plus UDL. Okay, so these are the three types of loads and corresponding conversion into the point load. Okay, so you can note down this first problem. Okay, so just wait. So in the second module, which is the equilibrium, so you will have these types of problem. So here first is problems on the objects hanging from the cables. Okay, so we have seen this type of problem where object is hanging with the help of cable. So first image, so object hanging from the ceiling, then weight supported by the crane hook. So this is again object hanging. Second type is problem on the spheres. Okay, so spheres, it is in the equilibrium with the help of the support given by the wall. Okay, then we have the problems on the ladders. Okay, so third image, and then we have the problems on the beams. So if you refer the syllabus for the module 2, so here you can see. So first is the coplanar forces, that is the equilibrium. So in that we have the concurrent. Okay, so we have seen the conditions of equilibrium for concurrent forces. then conditions of equilibrium for parallel forces and for the general forces. Okay. Then we have seen the concept of free body diagram. So if you solve any problem, whether on concurrent, parallel, or general force system, your first step will be you should draw the free body diagram. Okay, because free body diagram will have all the forces and the reactions. Then we have the equilibrium of beams. Okay, so in the equilibrium of beams, we have types of beams. Okay, so we have not discussed this yet. Then we have types of support. Okay, so we have just seen what are the types of support and the reactions for those supports. Then we have the problems on determination of reactions at supports for various types of loads. Okay, so we have just seen the different types of loads: point load, uniformly distributed load, and uniformly varying load. Okay, so this complete module, if we summarize, then we have the problems like so first will be the problem hanging from the cable, then we have the spears, then the ladder, and last is the beam. Okay, so in the equilibrium of connected bodies, so first problem in the concurrent force system that we have seen, so it is the equilibrium of connected body. Okay, so here two or more objects hanging with the help of the cables, two or more spheres connected to each other, then sphere supported using the ladder, then ladder held in the equilibrium using the cable, and beam supported using the cable. Okay, so in the equilibrium of connected bodies, you will have these types of problems. Okay, so all these problems, they will cover the parallel force system and the general force system, and also sometimes the concurrent force system. So here the first example, so just note down this. So question is determine. So this is the problem on the equilibrium of connected bodies. So determine the tension A, tension B, and the tension C to maintain the equilibrium. Okay, where the M1 is 10 kg and the M2, this is 15 kg. Okay, so we have to maintain this horizontal position for this cable. So let us take this. So this is AB, this point is C, okay, and this is the point B. And the angles are given. This angle is 25 degree and this angle is 30 degree. So to maintain this configuration, okay, Find out the tension A, B, and C. So here, when you draw the free body diagram, then you should draw the free body diagram for 2 points. One for point A and second for the point B. Okay. So this is the problem on the concurrent force system. Okay. So just draw the point A. So at the point A, the force is M1, which is a 10 kg. So we have to convert this 10 kg in Newton. So this is 10 into 9.81. Then next will be the tension in this cable AB. So when you show this tension at this point, show it directed away. So this is tension B. The next is tension A. Now this angle, so this is 65. Okay, so this is complete free body diagram for the point A. Now consider the point B. So at this point, this tension will be directed away from the point B. Then this is M2, which is 15 into 9.81. And this is the tension C. And this angle is 60 degrees. Okay. So if you observe, we have total 3 unknowns. Okay. So for each free body diagram, you can use two equations. Okay. One is summation fx and summation f1. So you can start from either A or B. So just consider the free body diagram. Point A. So use summation fx equal to 0, or you can use the Lamè's theorem. Okay. So if you use the Lamè's theorem, you can directly get the value of T and Tb. So from this, you can find out tension A and tension B. And if you consider the free body diagram for point B, you will get the value of tension C. Okay. Write down the next problem on the connected cables. So all these problems, they are based on the concurrent force system only. So question is, the string ABCD, it carries two loads P and Q. If force P is 50 kilonewton, find the force Q and the tension in the different portions of the string. Okay, so you have to find out the tension AB, tension BC, and tension CD. Okay, so only one weight is given, which is 50 kilonewton, and then we have to maintain the given equilibrium. Okay, so some angles are given. For the AB, it is 60. For CD, it is 30 degree. Okay, and this angle P and BC is a 75 degree. So use the proper conditions of equilibrium, draw the free body diagram, and get the value of these ranges.